All right. So not much has changed in the last few hours. Noting that our perceptions of time are different, me on this side of the video and you on that side of the video. But nothing's happened in these 3 hours since we talked about costs. Now we're talking about profit. So in general, a firm gets to choose both the inputs and the output level, right? Now, of course, you can't just choose the input and the output level independently. Whatever inputs you choose are going to implicitly determine the output level because there's a production technology which converts the inputs into an output at a fixed, using a fixed process that was given by this production technology, which is called F. Now, of course, you can't choose them completely independently, but you could think about this as a two-stage process. First, you choose how much to produce, and then you choose what's the most efficient way of producing whatever you just chose, right? And we're going to talk about how profit maximization is actually akin to that two-step decision-making process. First, choosing an output level, then choosing how to minimize costs to hit that target in the next video. But for now, we're just going to think of maximizing profit by choosing capital and labor, some combination of inputs, which is, of course, going to implicitly determine the output level. And what I mean by it gets to choose is it's not a constraint or a parameter of the problem the way it was in the cost minimization side. So a firm faces a cost for the inputs like it did before, and it also faces a price for the output. So this is saying how much can I sell my bushels of wheat for? I pay a cost for tractors at a cost for farmhands, and I sell wheat at a price in a marketplace. And this wheat is going to be the output that we're thinking of is more like wheat than it is like, say, iPhones, where Apple actually sets the price of the iPhone, right? So we're assuming price-taking behavior, as we have throughout the entire course up to this point, and it is an assumption that we will dispense with in the future and talk about monopoly situations where the firm can decide the price to sell at, right? So it faces the demand curve directly. Here, we're assuming that the firm does not make a dent in the overall demand, and therefore, when I sell my wheat into the marketplace, that doesn't change the price of wheat. So I'm a price taker. I just decide how much to sell for a fixed price, and I have no control over that price. This is the same assumption we've been maintaining since day one. So the goal of the firm is to maximize profit. And this is actually pretty close to the true goal of most real firms. Of course, they have different notions of profit. They care about dynamic problem and investing in technology and whatever. But the idea is generally that publicly traded firms have a fiduciary responsibility to their shareholders to maximize profit. And therefore, this is a pretty accurate interpretation of what the goal of a firm is. Now, what is profit? We're going to take a relatively simple view that profit is revenue from sales minus cost of production. Revenue from sales is the price of your output times how much output you produced. Cost of production is the cost of each of the inputs times however much input, that factor you demanded, summed up across the different inputs. And so it's going to look something like this. The profit, which we're going to denote by a pi is a P, Greek P for profit, and pi is really a function of the parameters also, right? So it's a function of the price vector and the costs. But taking the price and the vector and price and the cost vector as given, then the profit is a function of two choice variables, the capital and the labor, the capital input and the labor input, which of course implicitly determine the amount of production, which would be F of KL. Right? So if I hire K worth of capital and L worth of labor, then the resulting production is going to be F of KL. I'm going to produce that much output, and I sell F of KL worth of output at price P. So that first term in this equation on the left-hand side is the revenue. Revenue is the price times the output. F of KL is the output when I hire K worth of capital and L worth of labor. The right-hand term, the second term, is negative costs, and the cost is the price of capital times the amount of capital, K times CK, and the price of labor times the amount of labor, L times CL, or labor times price of labor. Whatever. Notice that if I want to maximize profit, I'm maximizing this function pi. This is not a constrained maximization problem. There is no constraint here. I can choose any amount of capital and labor. I mean, there is an implicit constraint about non-negativity, right? I have to choose positive amounts of this, but that's sort of a background constraint. This isn't a constrained maximization problem or minimization problem in the way that utility maximization or anything else was, right? Utility maximization was constrained by a budget. Expenditure minimization and cost minimization were constrained by utility or quantity thresholds, U bar or Q bar. This is not a constrained maximization problem. It's just a function that we're trying to find the maximum of. So this is actually a much simpler, in some sense conceptually simpler problem than the previous things we've worked with. So again, we're seeing that the production side of things is really boiling down to be simpler ideas than this utility business that we started with. Of course, nonetheless, we're still going to have the same first order conditions. We're going to see that, in fact, the ratio of things is about the same as it was before, and the interpretation is about the same. So on one side, we're going to have the marginal revenue, which is, of course, just the marginal production of your inputs, so the marginal productivity of your inputs times P, because you're no longer worrying about production, you're actually worrying about the price times the output. So that's on one side, and on the other side of the equation, you're going to have the marginal cost of hiring more capital and more labor in the event of capital. If we're talking about capital, then it's CK, right? If I hire a little bit more capital, I have to pay a marginal rate of CK. And this boils down, setting these two sides of the first order condition equal to each other, comes down to the old adage that marginal revenue is equal to marginal cost. I keep hiring inputs until the marginal revenue is equal to the marginal cost. Of course, by dividing this across my first order conditions, I also see that this means that the marginal revenue, the ratio of marginal revenues, which is P, cancels out on either side. So it's just the ratio of marginal productivities is equal to the ratio of marginal costs, which is the ratio of costs. And so that is we get back to the original first order conditions that we've seen over and over again, with this marginal rate of technical substitution being equal to a ratio of costs or prices. So let's take a look at this guy in a little more detail. So say that we have a cost function a la the previous lecture. So this function C is a cost function, which is the cost of producing a particular output at the optimal level. And remember, we had an example where the cost function had this cubic structure, right? It was first it was increasing and it was kind of concave, and then it keeps increasing, but it becomes convex. And there's this inflection point. That represented this idea that in the beginning, there's sort of easier to get, there's the low-hanging fruit in the production process, and then as you expend that low-hanging fruit, you have to go for more complicated production methods, which become more costly over time. So at first, there's returns to scale, positive returns to scale, and then later it's a decreasing kind of returns to scale, and the cost becomes higher. The revenue is a linear function of output, right? So the R in the top graph is just the price. The slope is the price of the output. If I produce twice as much output, I get twice as much revenue, right? Because I'm just selling it at this constant rate. This is the idea of being a price taker. There's a constant price of the output, and however much output I have is just scaled by that constant price. So I can look, what does it mean for the marginal cost to equal the marginal revenue? When the marginal cost is equal to the marginal revenue, it means the slope of these two lines is the same. It means the slope of these two lines is the same, right? Because the marginal cost is the slope of the cost line, the marginal revenue is the slope of the revenue line. So when the marginal cost is equal to the marginal revenue, or the ratio of marginal cost is marginal cost is equal to marginal revenue, the slope of these two things is the same, and so these two lines will be in parallel. And you can see that this happens twice in this particular graph, once at Q double star and once at Q star. We have 2 points in which the marginal cost is equal to the marginal revenue. Now, this is a first order condition, so at one point we're going to actually be solving for the profit minimizing vector, and at the other one we're going to be solving for the profit maximizing vector, right? And we can look at this by plotting on the bottom the revenue minus the costs. Revenue minus cost is profit. So you can see in the top graph, up until the point where they cross each other, the revenue is below the cost line, right? The cost line is exceeding the revenue line, so revenue minus cost is going to be negative. So up until the point where the cost and revenue line cross, in between Q star and Q double star, we have negative profits. Where they cross is the break-even point. Right? That's the break-even point where my cost is exactly equal to my revenue, which means I'm making zero profits. And then I keep going, costs keep increasing, but now they're below the revenue, right? my cost line is below the revenue line, and then they cross again at some other point where, again, I'm making zero profits, and then they stay above the revenue line forever, and if I continue to produce after that, I become negative, negative, negative profits. Each additional unit costs me more to make than I get in the marketplace. So the marginal cost is higher than the marginal revenue, which is the price of the output, P. Where is this maximized? It's maximized at Q star, where we have sort of the maximum difference between the cost line and the revenue line, right? So at this point, this is exactly the point where the additional unit becomes the most, producing one more unit costs exactly the amount that I would get if I sold that unit, right? So before that, each unit I sell costs less than each additional unit costs less to produce than I can sell it for. So producing more and more and more is giving me higher and higher profits. I get to this point where it's equal, the marginal cost is equal to the marginal revenue. Producing one more unit produces the cost of that production is the same as the revenue, so it's neutral and it doesn't do anything to my profits. And after that, the cost of producing one more is higher than I can sell it for, and so I'm losing money, right? And then the cost just explodes to infinity, and so I lose more and more money on each additional unit. You can see that as the profit function hits its maximum and then curves downwards very steeply. We usually assume that cost function is convex, or at least eventually it becomes convex, right? So that's just this C line in the top graph eventually has a convex shape. And when the cost function is convex, then the necessary conditions are also sufficient. The necessary, the first order conditions establish a maximum. There's never a minimum, right? So the reason this had a minimum at Q double star was the concavity of the cost function. Notice. The convexity of the C is kind of intuitive, right? If you think about something like petrol, as you're an oil company, you get some easy to reach reserves. You drill things that's very close to the surface. It's not too expensive. Doesn't cost so much labor. Doesn't cost so much technology. Once you've expended that, to go get the really deep oil requires a lot more, machines and people to operate the machines. And so that barrel of oil is much more expensive than the first barrel of oil. Is the idea. So the optimal inputs for a given a price and cost vectors is denoted by X star. So that's called the factor demand. So just like we had conditional factor demand, this is factor demand. It's not conditioned on having to produce a certain size output. And when you plug them into the production function, we get something called the supply function. So Q star is just F applied to the optimal quantity. So Q of P and C is the production when you're hiring the optimal amount of capital and labor, given a price and a cost vector, right? So this is a function. Q star is a function which tells you, given a price of an output and a cost vector for inputs, I'm going to do the optimal thing that maximizes profit. That optimal thing is given by this vector X star, which is an optimal amount of capital and an optimal amount of labor. X star is a vector of capital and labor. I plug that back into the optimized function in the same manner of an expenditure function or an indirect utility function. I'm plugging that back into the thing I'm trying to optimize, and I get something that's called the supply function of the firm, which says given prices and a price of the output P and cost of the inputs, the vector C, how much do I produce? And how much I produce is Q star of those costs. The profit function then is just the price times the optimal quantity produced minus the cost times the optimal input demand, which is just pi star, and that's just P times Q star, K star times CK, L star times CL. Okay, so you should stare at this and you should just see this is just plugging the optimal values back into the function you're optimizing. This is the same as the indirect utility function, the expenditure function, or whatever. So let's do one example and then we'll close out this lecture. So let the production function be given by A ln K, B ln L, right? So it's Cobb-Douglas again. We just split it up now. It's the additive form of the Cobb-Douglas rather than the multiplicative form. So the profit function is price times the production minus CK minus L. There's no constraint. This is not a Lagrangian. We're not doing a constrained maximization problem. This is all there is to it. How do you maximize something like this? You get to choose two variables. You get to choose C, and you get to choose K, and you get to choose L. Capital and labor, right? Those are the things you get to choose. So you have two first-order conditions. There's no first-order condition with respect to lambda, because there's no lambda, because this isn't a Lagrangian, because it's not a constrained optimization problem. So you take your first-order conditions, you get pi k and pi L, and notice that they don't depend on each other. You have two independent solutions, so you just can solve them individually. That's pretty easy, and you get a real nice K star is equal to A times the price divided by CK. L star is B times the price divided by CL. There's a nice symmetry there, so you could just solve one, you get the other for free if you look at that like variable replacement kind of scheme for solving for symmetric inputs. And now we have our K star and our L star. Now what do we want to do with that? We can plug it back into our F function, right? So we have our production technology. We plug in K star is equal to AP over CK for K, and we plug in L star is equal to BP over CL for L, and we get A ln K star plus B ln L star, and that gives us the optimal quantity produced when the price is P and the vector of cost is bold C. Then what I produce is A ln AP over CK plus B ln BP over CL. Okay, reading that is completely unhelpful. You should be able to see that that is just me plugging in K star and L star into the production function F. And then I can plug that itself into the profit function, and I don't know why I rearranged it. I promise you that is just P times Q star minus the costs CK times K, CL times L. But then you can rearrange it to get this thing. I don't know. I was trying to be fancy. I don't know why I did that. You can, you know, that's a good homework though. Exercise. Make sure you understand the algebra here that yields this particular equation for pi star. Now, what's nice about this is that we can do our comparative static exercises. Remember, comparative statics is how do these optimized quantities change as in response to changes in the parameters. So we have K star. K star was equal to here, AP over CK. So we're going to differentiate K star with respect to CK. What happens to the optimal quantity of capital demanded by the firm as an input into the production process when the cost of capital goes up? How many tractors do I buy when the price of tractors goes up, right? And you can see that the derivative is negative AP over CK squared, right? You square the denominator and you have a negative sign when you differentiate something in the bottom. So that's just an identity from calculus. So you should remember how to take derivatives of you know, quotients and things if you don't. And so you get this expression, and it doesn't really matter what the magnitudes are. The important thing is that, you know, here we can see that this is negative, right? It's negative because A is positive, P is positive, CK is positive, and there's a negative sign in front of the whole thing. And so we have that sort of as you would expect. If the price of tractors increases, I buy less tractors. When the price of tractors goes up, I hire less of that particular input. Now notice that this doesn't depend at all on the price of labor. The price of labor, and in fact, the optimal amount of labor and the optimal amount of capital were independent of each other. I hire that amount of capital and that amount of labor independent of the price of the other one, which means that if the price of capital goes up, I hire the same amount of labor as I was before, but I hire less capital, which means my entire production goes down, right? My production decreases because I have a monotone production function and I'm hiring less capital and the same amount of labor, which means I've decreased my inputs, which means my, my increasing production function must be less than it used to be. We can also look at, say, like a change in the price of an output, right? So what happens when the price of wheat increases? Do I hire more capital or more labor? And you can see here that the derivative of K star with respect to P is A over, that should be a CK, A over CK. That's positive, A is positive, CK is positive. And so when the price of a, when the price of wheat increases, I hire more capital. And of course, the same kind of logic says I hire more labor. I expand my farm when I face more favorable output prices. right? And again, that's very intuitive because I have this nice increasing production function, everything like that. One last point is that because they're unavoidable, a firm should ignore fixed costs, right? So if there's a fixed cost, like the cost of opening a factory, and I already paid it, it's fixed. I mean, to start production, it's done, it's there, I paid for it. I should always, I can't change the fixed cost. That's the definition of it being fixed, and that means I just should ignore it. I solve the same problem as if it wasn't there, and my optimal demands will be the same as if there was no fixed cost. And mathematically, of course, that just fixed cost doesn't depend on the variables. It's not variable, and therefore it drops out of first and second order conditions. Okay, so we'll pick up here with some sort of mathematical properties of these things that are very helpful for calculations and understanding the relationship between these different things that we've just, so I mean, now we've introduced many different things, right? Factor demand, conditional factor demand, cost functions, and profit functions, and we want to see, and the quantity supply function. We want to see how all of those things kind of mish and mash into each other, get a nice sense of duality, and then be able to make predictions from those kinds of things. And that's what we're going to do, and that's really the last topic in production by itself. And then we'll start talking about sort of market conditions. So production's easy, right? Cool.